All right, let's actually calculate the coefficient of static friction between something and another object. And I think that probably one of the most important ones I want to do is my shoe. Here we go. Here's a shoe. And I want to figure out the coefficient of static friction between this and some other object, maybe the floor, or I don't have a floor on me, but I have a piece of wood. And here's what this is. These rulers are set up here because I am super cheap and I don't have a protractor on me. I can't find one in my office anymore. So I use a ruler. This is my ghetto man's version of a protractor. Let's see what we can do. So I'm going to take the piece of wood, or the shoe, and put it on a piece of wood. Then what I'm going to do is I'm going to raise it up to a certain angle. Okay, I'm going to raise it up. Whoa, whoa. Right there, that was perfect. Let's actually mark that spot right there. One second. Put the shoe here. Here. Okay. Let's try it again. I'm going to put the shoe on the thing. There we go. I'm going to slide this across and raise it up until I get it to just start sliding. Right. Oh, there we go. That's perfect. That's what I want. That's at 21. That's at 38. Okay, so I was a little bit off the first time. 38, 21. The question is, how is this helping me figure out what the coefficient of friction is in between the shoe and the board? It's genius, really. I know, I'm that smart. It's because this is my incline. Actually, that looks terrible. Let me just grab the board. Here's my incline. I don't know if you can see that. Let's try it a little bit better. Maybe that pen's no good. Here's my incline. There, that's much nicer. And here's my shoe. Okay? And I know the angle at which it starts sliding. It's angle theta. And actually, I told you I'm going to use the ghetto man's version of the protractor because I don't have a protractor, but I do have a ruler, so I know that this is actually 30, the bottom right over here is 38 centimeters. 38 centimeters. And then the top over here, I didn't do this very well, but this goes up to about 20 and down to about 53, so that would be about 33 centimeters. So if I were to take the tangent of this angle, I would get the opposite over the hypotenuse, which would be 33 over 38. In order to figure out my angle, I would just say the angle is the tangent inverse of 33 divided by 38. Plug that into your calculator and figure out what you get. 33 divided by 38, since those numbers are pretty close to each other, I'm assuming it's close to 45 degrees, but I don't know, you can figure it out. And I would say that it's a little bit less than 45 degrees, maybe about 42 degrees. That's all I'm guessing though. All right, how do we figure out the coefficient of static friction in between here and here? Well, what forces are acting on this? Well, I've got the weight, okay? I've got my normal force normal. I've got my force of static friction, Fs. The reason why it's static is because this is right before it started to move, okay? And I also know, well, I guess the acceleration on this thing was 0 in every single case because I got it to the point where it just started to move. So it didn't move yet, but if I were to tilt it just a little bit more, it would start sliding. So if I wanted to figure out what the coefficient of friction between here and here is, I would simply, I would tilt my coordinate system, positive y over here, positive x over here. If I did that, then this would be angle theta. This right here would be my wx, or wy. sorry, wy, here's my wx. Looking at that right there, that says wy is equal to w cosine theta, sorry. This wx is equal to w sine theta. All right, that's just some information putting on the side over there. If I add up all the forces in the x direction, what is the acceleration of this thing in the x direction? Well, in the x direction, this thing has no acceleration because it's not sliding yet. That's why we're using static friction over here, because things not sliding, so this thing's equal to 0. Adding up the forces in the x direction, I see there's a negative Fs plus Wx is equal to 0. So what is Fs equal to? Well, that's negative mu s times the normal force plus Wx equals 0. What is my normal force? I don't know. I'm stuck. If I'm stuck at this point, I'll just turn over to the y direction. So now I'm going to add up the forces in the y direction. And that's equal to mass times acceleration in the y direction. This one is obviously 0 acceleration. Because even if it were moving, it's sliding down this way, but in the y direction, it's not moving anywhere. Adding up the forces in the y direction, I see that I have a normal force minus my wy is equal to 0. So my normal force is equal to my wy. Now I can combine this information here. I'm going to write down this equation, but instead of writing my normal force, I'm going to write wy. So I have negative mu s times wy plus wx is equal to 0. One of the things I forgot to do, by the way, is to get the mass of my shoe. I mean, wouldn't I need that information if I want to figure out the coefficient of friction between my shoe and this thing? Wouldn't the mass change that? Well, let's see. Wy is actually w cosine theta. So that's negative mu s w cosine theta plus w sine theta equals 0. Because wx is w sine theta. W is mg. Negative mu s times mg cosine theta plus mg sine theta equals 0. That's what the weight is defined as, is mass times gravity. There's a mass times gravity here, there's a mass times gravity here. I can factor out that mass times gravity. And I have negative mu s cosine theta plus sine theta mg equals 0. I just factored out that mg, I can plug that back in and I get the line right above it. But look at this, the m and g, if I divide both sides by m and g, what is 0 divided by mg? It's still 0, so I can just kill this thing right here. So I have negative mu s cosine theta plus sine theta equals 0. Or, maybe more to the point, is mu s cosine theta equals sine theta. All I did was I moved this over to the other side and made it equal to each other. So mu s is equal to sine of theta divided by the cosine of theta and that's my answer. I can figure out what theta is, and then I can figure out, well, if that's theta, whatever it is, 42, I take the sine of that angle, I take the cosine of that angle, and divide them. But here's the really trippy part, and that would give me my mu s, and they would have no units, because sine theta has no units, cosine theta has no units. Unitless divided by unitless is still a unitless number. But here's the part that would really freak me out, okay? Sine theta over cosine theta is actually equal to tangent of theta. So really, mu s is the tangent of theta, which I know if tangent of theta is equal to 33 over 38, mu s is really just 33 over 38. It's just my height divided by my horizontal distance. It's just the ratio of the angle. Really, mu s is just the angle. That's really interesting. All right, now, if the angle were bigger, okay, then mu s would have to be bigger. That's saying that if I could move the board up this high and my shoe doesn't stick, or the shoe doesn't move, that means the coefficient of friction between my shoe and the piece of wood is much bigger. Let's try something else. Let's try not my shoe, but let's try to do this. Let's do it upside down. So I got my shoe and it's upside down. This part should be the sticky part. This part shouldn't be the slidey part, or not be able to go up as much. And look, as soon as I get it to just this angle, which isn't very high, as soon as I get it to that angle, it starts to slide. So, you know, this part of your shoe is not as sticky, and this part of your shoe is super sticky. I hope that makes sense to you.